What if I told you that 253 million people worldwide are currently suffering from vitamin A deficiency? What's even more concerning is that this deficiency continues to be the leading cause of preventable childhood blindness, with up to 500,000 children going blind annually, particularly in Southeast Asia and Sub-Saharan Africa. There are numerous global initiatives like supplementation programs and the Golden Rice Project that have tackled this issue. And yes, they've made serious strides over the last 20 years, but they continue to lack economic incentive and, more importantly, sustainability. Communities need solutions that don't leave them dependent on foreign aid. In fact, a biological source of vitamin A that could be produced by the communities themselves would be a better alternative. My name is Sravya, and I'm going to be telling you how my project, Oviita, is a new synthetic biology approach to vitamin A deficiency. Oviita uses genetically engineered Yarrowia lipolytica, which will be grown in simple, locally made bioreactors similar to those used in local beer brewing seen in Africa and Asia. Y lipolytica is a food-safe, oil-producing yeast that has been modified to produce beta-carotene, which is the non-toxic precursor to vitamin A naturally converted in the body. However, to allow households to grow this yeast with minimal resources, I am further engineering it to produce cellulose-degrading enzymes, or cellulases, so it can be grown on readily available plant material. There are 3 classes of cellulase enzymes, therefore I will engineer 3 strains of Y lipolytica, each secreting one of the 3 enzyme classes. This will minimize the metabolic burden on each strain, and this approach has been done successfully in the past. When the 3 strains are cultured together, the secreted enzymes will sequentially degrade cellulose to glucose for the yeast to consume. The yeast can then be filtered and harvested from solution, cooked, and added to food as a vitamin A-rich supplement. At a molecular level, the selected cellulase genes were put together with a strong promoter and a secretion tag for high production. Furthermore, they've been modified for better functioning in Y lipolytica as the optimal temperature and pH for activity has been changed. This was done through protein modeling and engineering. I'm currently in the process of introducing the cellulase genes to the Y lipolytica genome, after which cellulase production will be confirmed through SDS-PAGE and ELISA experiments. Meanwhile, to verify the general idea of the cellulase system, I decided to see if Y lipolytica could grow in cellulose-based media with commercially supplied cellulase. In the initial growth tests, I found Y lipolytica successfully able to grow with glucose concentrations as low as 0.02 milligrams per milliliter, which is over 100 times less than what is in standard yeast media. Furthermore, a DNS assay revealed that even 1 milligram per milliliter of commercial cellulase was able to produce 50 times this amount of glucose from pure cellulose. Therefore, once the cellulase genes are introduced to Y lipolytica, these are the thresholds for cellulase and subsequent glucose production that will have to be met to maintain a culture. Evidently, previous literature has found engineered Y lipolytica to produce 20 to 100 milligrams per milliliter of cellulase enzyme, which is much higher than what I found to be required. Next, when I grew Y lipolytica on boiled straw and chickpea shells with supplied cellulase, I saw cell growth increase over the first 2 days and then dramatically drop compared to the pure cellulose media. I believe this was because the crude cellulose became less accessible to the cellulase as time went on, resulting in less glucose production and subsequently cell death. This indicates that the cellulose material will have to be mixed regularly, changed often, or a more fleshy plant source like leaves should be used to provide better sustenance of the yeast culture. Once the engineered strains are made, I will repeat these cellulose growth experiments with the co-culture and characterize the activity of the cellulases through a glucose test. Now you may be wondering how receptive the people may be to eating GMOs, especially considering the attempts of the Golden Rice Project. However, through discussions with anthropologists and local organizations, I've learned that GMO stigma is not as prevalent in the people when the product has a tangible benefit, and therefore hopefully will not be a significant barrier to Oviita. So, learning from the last few decades of VAD mitigation, we now know we must start collaborating with VAD communities to tackle this problem instead of just imposing solutions. Once implemented, Oviita will provide a sustainable and inexpensive solution to vitamin A deficiency, empowering communities to address their own health needs.